Welcome! In this session, we will tackle LeetCode problem number 942, titled DI string match. This problem involves reconstructing a valid permutation of integers from 0 to n based on a given string pattern. Let's dive in and explore how to efficiently solve this interesting problem. In this problem, you are given a string S composed of the characters D and I. The length of this string is n, and it represents a specific pattern that a permutation of integers from 0 to n inclusive must follow. The goal is to construct one valid permutation that satisfies the conditions described by the string. Here, each character in the string determines the relationship between consecutive numbers in the permutation. If the character is D, the next number in the sequence must be less than the current number. On the other hand, if the character is I, the next number must be greater than the current number. The input to the problem is the string S, and the output is a list of integers that forms a valid permutation. If there are multiple valid permutations, you can return any one of them. Let's look at an example to understand this better. Suppose the input string S is IDID. The task is to construct a permutation of the integers 0, 1, 2, 3, 4 that satisfies the conditions in S. Here's how we can do it. The first character is I, which means we need to select the smallest available number first, followed by the largest available number. So, we start with 0 and then choose 4. The second character is D, so we pick the largest remaining number, which is 3, followed by the smallest remaining number, 1. By continuing this process for the remaining characters, we get the permutation 0, 4, 1, 3, 2. This satisfies the conditions in the string and is one valid solution. Now, consider another example where the input string is 3. Here, all the characters in S are I, meaning the permutation must be in strictly increasing order. Starting with the smallest available number, we sequentially select 0, 1, 2, 3. Since there are no D characters, there's no need to choose any numbers in descending order. The result is 0, 1, 2, 3, which satisfies the increasing pattern defined by the string. In contrast, take the string DDI. Here, the first two characters are D, so the first two numbers in the permutation must be in descending order. Starting with the largest available number, we choose 3, followed by 2. The next character is I, so we switch to selecting the smallest remaining number, which is 0, followed by the next largest, 1. This gives us the permutation 3, 2, 0, 1. Notice how the solution alternates between descending and ascending patterns based on the instructions in S. Finally, there are some constraints and edge cases to keep in mind. The length of the string S is at least 1 and can go up to 10⁻⁵. Each character in the string is either D or I. The output permutation must include all integers from 0 to n exactly once, ensuring it's a valid permutation. For edge cases, if all characters are I, the permutation is strictly increasing. If all characters are D, the permutation is strictly decreasing. For alternating sequences like itidid, the solution alternates between the smallest and largest remaining numbers, resulting in a pattern like 0, 6, 1, 5, 2, 4, 3. These examples highlight how the problem handles a variety of input patterns within the constraints. To solve LeetCode problem number 942, the goal is to reconstruct a permutation of integers from 0 to n inclusive based on a given string S, which consists of the characters D4 decrease and I4 increase. Each character in the string specifies a relative ordering between consecutive elements in the resulting permutation. One approach to solving this problem is the brute force method, where we generate all possible permutations of numbers from 0 to n and check if each one satisfies the ordering dictated by the string S. While this approach directly aligns with the problem requirements, its computational complexity is extremely high, n+1. *n, due to the factorial growth in the number of permutations. This makes it impractical for larger inputs, as the time required grows exponentially. Although conceptually simple, this method highlights the need for a more efficient solution. A more practical and efficient approach is the two-pointer technique. Here, we use 2 pointers, low and high, initialized at 0 and n, respectively. As we traverse the string S, for every I, indicating an increase, we place the value of low into the permutation and increment it. For every d, indicating a decrease, we place the value of high and decrement it. At the end of the traversal, the last remaining value of either low or high, as they will be equal, is added to complete the permutation. The intuition behind this approach is simple: use the smallest available number when the order must increase and the largest when it must decrease. This method runs with a time complexity of O(n), as it processes the string in a single pass, and requires O(n+1) space for the result. It guarantees correctness and is straightforward to implement, making it the most efficient solution. Additionally, there are greedy alternatives, such as using a stack or a priority queue to track available numbers, but these tend to be slower, with complexities ranging from O(n log n) to O(n squared, and are less optimal for this specific problem. The two-pointer technique emerges as the optimal strategy for solving this problem. It is both intuitive and efficient, perfectly addressing the constraints and requirements. By assigning the smallest available number 4i and the largest 4d, we satisfy the conditions in a way that eliminates unnecessary computations. Key insights include recognizing that the I and d characters directly correspond to the smallest and largest in used numbers, respectively. The use of two pointers ensures that we can track these values efficiently without requiring additional sorting or complex data structures. This approach is particularly appealing because of its efficiency, achieving O(n) time complexity, which is ideal given the constraints. It is also simple to implement, requiring only basic arithmetic and a single traversal of the string. Additionally, it scales well, handling the largest input sizes comfortably within the problem's constraints. While the two-pointer technique is highly efficient, it is worth noting one trade-off: it produces only one valid permutation, not all possible permutations. However, this is entirely acceptable since the problem explicitly asks for any valid permutation, not all of them. This slight limitation does not detract from the method's effectiveness, as it delivers an optimal solution in both time and simplicity. In conclusion, the two-pointer approach is undoubtedly the best choice for solving LeetCode problem number 942. It balances efficiency, correctness, and ease of implementation, making it a practical and reliable solution for this permutation reconstruction task. To solve the DI string match problem, we need to build a permutation of integers ranging from 0 to n, where n is the length of the input string s. The string s consists of the characters d and I, which stand for decrease and increase, respectively. These characters define the order relationships between consecutive elements in the permutation. To achieve this, we start by initializing two pointers, low and high, to 0 and n, respectively. These pointers will help us keep track of the smallest and largest values available for constructing the permutation. We'll also create an empty list called result to store the final permutation as we build it step by step. The next step involves iterating through each character in the string s. If the character is I, it means we need to append the smallest available value to the permutation. In this case, we append the value of low to the result list and then increment low by 1. On the other hand, if the character is d, it indicates a decrease, so we append the largest available value, which is high, to result in decrement high by 1. After processing all the characters in the string, we will have one remaining value either low or high, as both pointers will have converged. We append this final value to result to complete the permutation. Finally, we return the result list, which now contains the desired arrangement of integers from 0 to n that satisfies the constraints defined by s. This algorithm relies on some key insights to work efficiently. First, the use of the two-pointer technique allows us to directly select the smallest or largest remaining value as needed, without additional computation or sorting. This makes the approach straightforward and efficient. Second, the algorithm employs a greedy strategy. It makes the optimal choice at each step by appending either the smallest or largest value to match the current constraint, ensuring correctness. In terms of efficiency, the algorithm operates in O(n) time, as we traverse the string s once and perform constant time operations at each step. For data structures, the result list is used to store the permutation, as it supports efficient appending in O(1) time. The low and high pointers ensure we keep track of the range of available numbers, making the solution both clean and effective. The algorithm performs two key operations repeatedly. The first is appending either the value of low or high to the result list, depending on whether the current character in s is I or d. This guarantees that the permutation respects the given constraints. The second operation is updating the pointers. Incrementing low or decrementing high narrows the range of available numbers, ensuring no value is reused. The algorithm handles various edge cases seamlessly. For instance, if the input string s is empty, the result is simply 0, as there are no constraints to satisfy. For strings consisting entirely of I or D, such as s equals I or s equals d, the algorithm produces ascending or descending sequences, respectively. It also handles mixed patterns like s equals ID by alternating between the smallest and largest values as needed, constructing a valid permutation that adheres to the constraints. Let's analyze the algorithm's complexity. The time complexity is O(n), where n is the length of the input string s. This is because we iterate through the string once, performing simple operations at each step. The space complexity is also O(n), as the result list stores the permutation of size n plus 1. Now, let's walk through an example. Suppose the input string is s equals ID. Initially, we set low equals 0, high equals 4, and result equals. For the first character, I, we append low, 0, to result, then increment low to 1. Next, for D, we append high, 4, then decrement high to 3. For the following I, we append low, 1, and increment it to 2. For the final D, we append high, 3, and decrement it to 2. At this point, low and high are both 2, so we append the final value to result. The resulting permutation is 0, 4, 1, 3, 2. The output for this example is 0, 4, 1, 3, 2. This permutation satisfies the constraints defined by the input string s equals ID, where each I corresponds to an increase and each D corresponds to a decrease. The algorithm efficiently constructs this solution using the two-pointer technique, ensuring correctness and optimal performance. With linear time and space complexity, it is well suited for handling larger inputs. This concludes our detailed exploration of the DI string match problem and its solution. The provided Python solution solves LeetCode problem number 942, DI string match, which involves constructing a permutation of integers from 0 to n plus 1 that satisfies the order defined by the string s, containing D4 decrease and I4 increase. The goal is to generate the result in O(n) time complexity. Hashtag code walkthrough. 1. Initialization. The low and high variables represent the smallest and largest numbers in the range 0, n, where n is the length of the input string s. They are initialized to 0 and len s, respectively. 2. Result list. An empty list, result, is initialized to construct the permutation step by step. 3. Iteration over s. The code iterates through each character of the input string s. If the character is I, increase, the smallest available number, low, is appended to result, and low is increment. If the character is D, decrease, the largest available number, high, is appended to result, and high is decrement. This ensures that the relative ordering defined by s is maintained. 4. Appending the last number. After processing all characters in s, one number, the only remaining number in the range, is left. Since low and high converge to the same value, appending either low or high completes the permutation. 5. Return the result. The constructed result list is returned as the output. Hashtag efficiency. Time complexity, O(n), where n is the length of the string s. The algorithm processes each character of s exactly once. Space complexity, O(n plus 1), for the result list. Hashtag example. For input s equals ID, the solution produces low equals 0, high equals 4 initially. Iteration, I-append 0, D-append 4, I-append 1, D-append 3. Final append remaining number, 2. Output, 0, 4, 1, 3, 2. This approach guarantees correctness while maintaining optimal performance. This is the Java implementation of LeetCode problem number 942, DI string match. The logic mirrors the Python solution, using two pointers, low and high, to generate the permutation based on the characters I and D in the input string. In Java, type declarations are required for variables and arrays. The char@* method is used to access characters of the string, and we utilize an integer array to store the result. The overall approach remains the same, ensuring efficiency and correctness. To solve this problem, we begin with the input string s equals id. First, we initialize three variables, low equals 0, high equals 4, since the length of s is 4, and an empty array result to store our output. We then iterate over each character in the string. For the first character, char equals I, which stands for increase, we add the smallest available number, low, to the result array. This updates result to 0, and we increment low to 1. Next, for the second character, char equals d, which stands for decrease, we add the largest available number, high, to result. This updates the array to 0, 4, and we decrement high to 3. Moving on to the third character, char equals I, we again add the current value of low to result, updating it to 0, 4, 1, and increment low to 2. Finally, for the fourth character, char equals d, we add the current value of high, updating result to 0, 4, 1, 3, and decrement high to 2. At this point, the iteration is complete, but we still have one number left, as low and high are now equal. We append this remaining number to the result array, updating it to 0, 4, 1, 3, 2. This gives us the final output for this example, 0, 4, 1, 3, 2. Now, let's go through another example with s equals 3. Again, we start by initializing low equals 0, high equals 3, and an empty result array. As we iterate through the characters, the first character is char equals I. We add the current value of low to the result, updating it to 0, and increment low to 1. The second character is also char equals I, so we repeat the process, appending low to result, which becomes 0, 1, and incrementing low to 2. For the third character, char equals I, we add low again, updating the array to 0, 1, 2, and incrementing low to 3. When all characters in the string are processed, we are left with one final number, which is low. We append this to the result array, updating it to 0, 1, 2, 3. The final output for this example is 0, 1, 2, 3. Let's now consider one more example where the input string is s equals ddd. As before, we initialize low equals 0, high equals 3, and an empty result array. For the first character, char equals d, we add the current value of high to result, updating it to 3, and decrement high to 2. The second character is also char equals d, so we repeat the process, appending high to result, which becomes 3, 2, and decrementing high to 1. For the third character, char equals d, we add high again, updating the array to 3, 2, 1, and decrementing high to 0. Finally, we append the last remaining number, which is low, to result, updating it to 3, 2, 1, 0. The final output for this example is 3, 2, 1, 0. The time complexity of the solution is determined by analyzing each step of the algorithm. First, initializing the variables low, high, and the result list only takes constant time, which is 0, 1. The main computational effort comes from iterating through the string s. Since the string has a length of n, the loop runs n times. For each character, we perform a few operations, comparing the character to I or D, appending a value to the result list, and updating either low or high. Each of these operations individually takes 1 time. Since they are executed once per character, the total cost of the loop is n. Finally, after the loop, the algorithm appends one remaining number to the result list, which is another 1 operation. When we combine all these parts, the overall time complexity simplifies to 1 plus n plus 1, which is n. Analyzing the space complexity, the input string s is provided as an argument and does not require any additional space allocation, so it does not contribute to the space complexity. The variables low and high require only constant space, which is 1. The result list, however, is used to store the final permutation. Since the result contains n plus 1 elements, where n is the length of the string s, it occupies n space. Additionally, the algorithm does not use any auxiliary data structures beyond the result list. Therefore, the total space complexity is dominated by the result list, resulting in n. To compare this optimal approach with the brute force method, consider the naive solution. A brute force approach would involve generating all possible permutations of the range 0, n, which contains n plus 1 permutations. For each permutation, we would check whether it satisfies the DI constraints. This leads to a time complexity of O(n plus 1), due to the factorial growth of permutations. The space complexity for the brute force approach would be O(n), to store the current permutation being checked. In contrast, the optimal solution avoids generating permutations entirely and directly constructs the result in linear time. This reduces the time complexity to O(n) and the space complexity to O(n), making the current approach far more efficient. Moreover, the best, average, and worst-case time complexities of the optimal solution all remain O(n), as the algorithm always processes the string S in a single pass, performing a fixed number of operations per character. To mathematically justify the time complexity, we observe that the algorithm processes the string S exactly once. For each character in S, it performs a constant number of operations, such as comparisons and updates, all of which take O(1) time. Since the number of characters in S is n, the total number of operations is proportional to n, resulting in a time complexity of O(n). For space complexity, the primary contributor is the result list, which stores n plus 1 elements. This means the space required grows linearly with the size of the input, leading to a space complexity of O(n). Together, these analyses confirm the efficiency of the algorithm in both time and space usage. When solving the DI string match problem, there are a few common mistakes to watch out for. First, it's easy to confuse how to assign values for D and I. Remember, D means the sequence must decrease, so you should assign the largest available value next, while I means the sequence must increase, and you should use the smallest available value. Mixing these up can lead to incorrect results. Another frequent error is off by 1 mistakes in the result array size. Since the input string has n characters, the output must contain n plus 1 numbers, spanning from 0 to n inclusively. Failing to account for this results in a permutation that's too short. Lastly, some misunderstand the concept of a valid permutation. While there may be multiple valid sequences that satisfy the constraints, the output must follow the rules of the problem deterministically, rather than relying on random selection or assumptions about correctness. Another pitfall is relying on inefficient brute force methods. Generating all permutations of 0, 1, n, and checking each one against the input pattern is not practical. This approach has factorial time complexity, which quickly becomes computationally infeasible as n grows. It's crucial to adopt more efficient strategies. Additionally, edge cases can trip up solutions that aren't thoroughly tested. For instance, if the input string is empty, the output should simply be 0. For strings like III or DDDD, which contain only I's or only D's, the solution must still generate a valid sequence efficiently. These edge cases highlight the importance of handling extreme scenarios gracefully and avoiding assumptions about the input structure. This problem is a great example of a greedy algorithm in action. By assigning the smallest and largest values incrementally as you process the input pattern, you can achieve a solution with linear time complexity. Recognizing this pattern is key, as many constructive algorithm problems involve systematically mapping the input description to an efficient assignment strategy. For interviews, it's also helpful to explicitly discuss edge cases, such as empty strings or monotonous patterns like all I's or all D's. This demonstrates thoroughness and attention to detail. You should also emphasize the efficiency of the greedy approach, which avoids the unnecessary computation of brute force solutions. If you're looking to deepen your understanding, you might explore related problems like LeetCode 986, which uses a similar greedy approach for interval intersections, or LeetCode 484 and 135, which also involve constraints and resource allocation using constructive or greedy methods. There are alternative approaches to solving this problem, each with its own trade-offs. A common strategy is the two-pointer approach, where you maintain two indices low, starting at 0, and high, starting at n. Depending on whether the current character is I or D, you assign values from either end, progressively narrowing the range. This method is simple to implement and avoids using additional data structures, though it might feel less intuitive for beginners. Another option is pre-computing the full range of numbers, 0, 1, n, and then reordering them based on the input pattern. While easier to code, this approach can be less efficient due to unnecessary rearrangements. Lastly, there's recursive backtracking, which explores all possible sequences to find one that matches the pattern. However, this method is highly inefficient with factorial time complexity, making it unsuitable for larger inputs. Each approach offers valuable insights but highlights the importance of efficiency in problem solving. Great work! To recap, we solved the DI string match problem using a two-pointer technique, achieving optimal efficiency. Remember to practice similar problems to solidify your understanding. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!